What is the error? Which is fine. Yeah, that's okay. That's okay. Yeah, because we need just one app from there, and that builds properly. Yes. Yes. For the other ones, we don't have the dependency installed, so just don't bother.
It also gives me, when I run the last email, it also gives me a connection.
So it seems like Toronto is connected right now.
Yep. Yeah. Thank you.
Yeah. All right. So, and everyone can hear me loud and clear in Toronto? We cannot hear you, Laval.
She just showed the sign. She can hear you.
Sorry, Laval can hear us. Okay, all right. So okay, then I guess at this point we can start our lab. So hello everyone. So today's lab will be focused on control plane, in contrast to data plane that we went through last week. So at this point, I have shared the lecture materials for today on Piazza. So you can download it from Piazza, and those of us like who were not connected for this time. So if you could go to slide 7. There is an environment setup phase. Maybe like while I'm introducing the ONOS controller and everything, run the environment setup script on your virtual machine. So hopefully by the time we start, everything will be set up. So I'm going to the slide. Okay, just a second. And everyone can see my screen at this point, correct? Yeah. Okay. All right. So I'm starting from slide 3. So the VM is the same VM. You have the credentials already. Just a quick recap on SDN and OpenFlow. We have so the concept of SDN is that the control plane is separated from the data plane, correct? And we have this OpenFlow protocol coming for communication between control plane and data plane, and also that provides a specification for the OpenFlow switches. Now, our first week was focused on data path, and we used CLI tools, CLI tools for Open vSwitch. So Open vSwitch is a software implementation of an OpenFlow switch. So we used CLI tools for Open vSwitch to manipulate the data path. Right? We queried the data path. We were able to add flow rules to the data path, read statistics and whatnot. So today we'll look at ONOS controller. So ONOS stands for Open Network Operating System. It's a control plane. It's a controller application. So the main focus of today's lab will be to control the same network, similar network, from the control point, from the control plane, without using the CLI. Now, a quick introduction to ONOS. This is taken from the video lectures that was posted for the first course. If someone is not taking the first course, I'm just giving a quick overview of what ONOS is. So, in the figure, this is like a high-level architecture or high-level view of ONOS. So, how ONOS looks like. So at the very bottom, we have a communication layer, which is responsible for communicating with the data path or the switches. So typically, this will implement different protocols that talk to the data path. So mostly OpenFlow. It was targeted mostly towards OpenFlow, but there are implementations of other southbound APIs as well. Then we have a layer that actually manages the network-wide states, like a global network view of the topology, the hosts, the links, also statistics, counters, and whatnot. Right. So that's the network-wide state management layer. And also on top of it, there is a set of APIs that ONOS provides for development of control applications. So ONOS comes with some very fundamental like control applications, like ships with them. But on top of that, it has APIs. So someone can write their own control applications. For instance, say a traffic engineering application geared for a specific network. So someone can write that using that API. And ONOS has also this thing called an intent framework. So the idea of an intent is that it's a very like from a very high level, a programmer specifies what the program wants from the network. For instance, it can specify that, okay, I want connectivity between this host and this host, without necessarily specifying how this connectivity will be ensured. That is handled by the controller. So this is like a high-level programming abstraction provided by ONOS. So ONOS has a Java API for specifying different kinds of intents. So we'll see an example of like a built-in intent during today's lab exercise. And finally, one thing to mention is that so ONOS is implemented as a distributed controller. So the layer in the middle that we are seeing, which is managing the state of the whole network, this layer is designed as a distributed software from scratch, using and ensures consistency of the data and whatnot. So a quick look at how this distribution is performed. So at the very core of this distributed framework is, so ONOS implements a data store, a distributed data store. And there are different subsystems in ONOS. For example, like there is a subsystem that manages topology. There is a subsystem that manages statistics, for instance. So each subsystem, it can store its state. For instance, the network topology or counter values in this distributed store. And the distributed store can provide different levels of consistencies to the different subsystems. Like, say, for topology, it always requires an up-to-date view of the topology, right? So there are primitives in the distributed store that allows always a strongly consistent view of the topology to the topology management subsystem. So it implements a Raft, a protocol called Raft, which is a consensus protocol for performing distributed transactions. So even though multiple instances of ONOS, they're updating the topology, this protocol ensures that there is always a strong, consistent view of the protocol available to all the instances of the topology manager. And also there is a gossip-based consistency protocol implemented by ONOS. This is for eventually consistent state. So states that are not as urgent as the topology, for example, like counters. If we miss some values for a couple of seconds, maybe that's okay, depending on what counter it is, right? So this distributed state implements different consistency protocol and also provides different abstractions to write data to different for different consistency levels. So this is the core of ONOS's distributed network-wide state management layer. Now, definitely we can run multiple ONOS instances, and they can be run in a cluster of machines for better performance and also for fault tolerance as well. And different ONOS instances, they can control like subset of network devices. And given that there is a distributed data store for state consistency, somehow the consistency of the data, it is ensured, like everyone gets a global network view. So I'll not go further into the details of how the internals are implemented. I'll stop here, but is there any question from anywhere? No? Okay, all right. So if there is no more questions, then I'll proceed to our lab today. So ONOS controller has already been downloaded inside the virtual machine, so we don't have to download the controller itself. So for the environment setup, we just need to update the version of Java that is inside the virtual machine. One of the reason is, so later on during the exercises, on the third week, we'll actually look into FlowVisor. That requires an older version of Java. So we'll update the version of Java today and downgrade next week. So that's the reason we are going through this environment setup phase for today. So did it work okay for everyone? Okay. So was everyone able to download the script, run it, probably saw an error?
We do have some errors here.
Pardon me, can you please repeat?
Here we have some error. Can you guys?
You have some errors here? Okay, all right. So maybe one of you can just share your screen. Is that possible?
No.
Because, okay, so you will see an error for the build phase. Like you'll see a list of tables, like a table with multiple rows, and at the end you'll see an error. If you see that, that's fine.
You guys have something? Try to connect to see. Okay. Okay. Yeah, you can try.
But I think you have to.
See how it?
Yes.
One of us will show our screen, our laptop in front of the camera.
Okay.
Not sure you can see, but yeah, he will try.
All right.
Yeah. I don't know. He just.
It's clear?
Yeah, that is actually quite clear. Okay. No, not very clear actually. I see. So let's try to do one thing. Can you see my screen?
Yeah.
Yes.
Okay. So everyone, check your Java version. You would see something like this. Yes. So
Yes.
Yes. Everyone?
Let's see.
Yeah. So for ONOS, we'll need Java version 1.8 or above.
We have someone who hasn't.
Yes. So I think that he who showed me the screen, he doesn't have this Java version, right?
Yes, he has 1.7.
1.7. Yeah. So can you please update your Java version? So if you run the environment setup script that it provided, it will update your Java version.
Okay.
But for everyone else, so if you have this Java version, then we are good to go. Okay. All right. So other schools are we doing okay? Okay, I don't see any response from Toronto or Laval.
We're all good here in Toronto.
Here, Waterloo. Good, we're good. Okay, all right. So let's.
Wait, Shabot, I think the Leslie she does have a problem connection.
Okay.
So okay, let me try to contact with you.
We have.
Okay, how did you get the new version of the
I'm trying. I didn't know.
Someone posted a question on Piazza regarding the some ONOS error.
On Piazza.
Yeah.
Okay, let me check.
1.8.
Okay. So are we still waiting for Laval? Okay. Okay. All right. Okay. So then let us proceed. I think they're connecting via wired line. Okay. All right. So yes. The Java version still shows 1.7. So at the beginning of the script, there is a part for just Java, like updating to Java 8. Just copy that part and run that part. Okay. Where is the slide? Okay. Okay. So if everyone has correct version of Java, we can start the controller. Okay. So on slide 7, we have the command to start the controller. So let's copy the command and start our controller. Okay. So if the controller successfully started, then everyone should be able to see a screen like this with a ASCII art drawing ONO, like the logo of ONOS. Can everyone see that?
Yes.
Yes. Toronto and Laval,
Toronto's good.
we're good. Okay. Waterloo? Yes. Yes. Okay. All right. So we're on the same page. So we have started the controller. Now let's check what's next. Oops. So we have a controller. Now let's also have a network, right? Because we need a network to control. So I have a command here to deploy a very simple network. So let's open a new terminal window and deploy a linear topology. Wait. So I'm opening a new terminal window and deploying a linear topology. Yeah, so the command is given in the slides using the same command to deploy the topology. Just one quick note. So I'm adding these two extra options with Mininet. So the first option, --ARP, it will actually populate the ARP table at the hosts. So then whenever we are trying to actually send packets, path for ARP packets won't be like required to be set up. So because the ARP tables at the host are already populated. And the last option, --Mac, this is actually for convenience. This option actually makes sure that the MAC address of the interfaces, they look nice. Nice as in like starts from all 01, all 02, all 03, something like that. So it's easier to map between a host and its MAC. Like we can look at a MAC and say, okay, this is host 1 or host 2. So this is just for convenience. So deploying the topology. And also notice here that I'm specifying a controller option here and saying the controller should be remote, and also specifying the IP address here. Like I think in our previous during our previous lab, we are not really using an external controller. So this is how we specify an external controller in Mininet, just with this controller option. So with that, oops. All right, so with that, we have deployed the network. Now, let's try to do some query from the control plane. So now we have a controller deployed, listening on a port. We have deployed a network as well, specified a remote controller at that specific port. So there should be some communication between the control plane and the data plane, right? So let's clear up the screen for ONOS controller, just so that we can have a better view of what's happening here. So there is a command called devices, right? So right now we are at ONOS CLI, the control plane. So the control plane, we have this command devices that will show us the list of devices that the controller has recognized. So essentially the list of switches, right? Now we deployed a linear topology with 4 switches. So we should be able to see 4 switches here. But unfortunately, we don't see anything, correct? I guess for everyone, this is the same case. So when you execute this devices command from the ONOS CLI, you don't see anything. Empty output, correct? Other schools?
Yes.
Yes?
Yeah.
Right? Okay, all right. So the reason is the way ONOS operates is everything in ONOS is actually an application. Even the OpenFlow protocol itself, it is implemented as a driver that should be deployed as an application. The routing, forwarding, everything is written as an application. So right now, ONOS does not have any application installed or activated. So even like the most basic OpenFlow operation, like discovering the switch, it doesn't work. So how can we install an application or see what applications are installed? So for that, So for that, we have two subsystems in ONOS. One is the apps, the other one is just app. As the name suggests, apps is for multiple apps. This is for mainly listing what applications are there, what are installed and what not. And the other command app, this is for adding new applications or activating new applications. Okay, so let's see what applications we currently have in our system. For that, the command would be apps with two options, -s, -a. -a for just show us the active ones, and -s for using like a short name for the application, not really using like long, fully qualified Java package names. So at this point, everyone should see an output something like this. There is just one application installed, like a basic drivers. There is nothing else activated or installed in ONOS. Okay, I think this should be, since we didn't see anything when we ran devices command, this is probably every one of us will see something like this in the output. So then our first step is let's activate OpenFlow with ONOS, right? So this means that activating the OpenFlow application in ONOS. If you go to the slide, if you go to slide 10, this is how it looks like the command looks like for activating an application. So we have this command app for activating, deactivating applications. So app activate, and then the fully qualified package name for that application. So let's take that and activate our OpenFlow application here. Right. Okay. So we activated the OpenFlow application. And let's, list the active applications. So as you can see, we now have more entries, right, when we list all the applications. And this OpenFlow based application is part of that. So at this point, we should be able to see something like this when we run devices. So previously, when we executed the devices command, there was no output. It was empty. But right now, when we execute devices command, we see some output, right? There are some entries that is displayed. I think the lines kind of broke very bad here because of the size of the screen, but let me highlight at least one of them. Oops. Okay, so each row represents a switch in the network, right? And we have a switch ID or data path ID. We can see also things for example, what kind of protocol is supported by the switch. That's the last entry. So this switch supports only OpenFlow 1.0 protocol, which makes sense because, right, I think in this VM we have Open vSwitch version 2.0.2, which supports only OpenFlow 1.0, not really the other protocols. And also the manufacturer of the switch, the hardware name and whatnot. So this is all the information displayed for the switch. Now, so what does it mean? This means that as soon as we activated this OpenFlow application here, ONOS could respond to the switches, right? Because we started the switches, they were given a controller IP and port number. They were trying to communicate with the controller, but the controller did not have the necessary driver to reply back to the switches, right? So the switches they were trying to send a hello request, like OpenFlow hello, but could not get a hello reply back. So as soon as we installed the driver, there was a two-way communication between the controller and the switch, and that's how the controller recognized the switches, right? Now, let's open another window. So we'll just quickly look at the OpenFlow messages that are exchanged between a controller and the switch. So there is a packet capture tool here, Wireshark. Let's run Wireshark from the other terminal window. You need to run Wireshark in super user mode, otherwise it won't be able to capture packets. All right, okay. So so on the top left corner, there is a button that shows you the list of interfaces where we can capture traffic. Let's select loopback interface here because all the communication is happening locally, correct? Select the loopback interface and start capturing packets. We'll see a lot of packets going around. So what we can do is we can put a filter here to filter just the OpenFlow packets because we are just interested in seeing OpenFlow packets, right? In fact, I think I have a filter in my slide to show you OpenFlow feature request packets. So let's go there. Okay, so my screen is very weird. Okay, I found my mouse. So I'm taking the filter that I put into the slide and putting the filter here on the top bar and apply. So there is no message here because we started packet capturing after we connected with the switches, right? So let's keep the packet capture thing open and try to reconnect the switches. So let's go back to Mininet. Just quit from here. All right. And just try to deploy the same network again. All right, so we should, yes. So if you stopped Mininet and deployed the network again, after the network started, and if you go back to your Wireshark window, so you'll now see like a list of messages. So these are messages that are like examples of messages that are exchanged between the control plane and the data plane when the switches they boot up. For example, there is this OpenFlow feature request message. Can everyone see my screen? Or if you look at your screen, you'll see that, okay, in Wireshark, you have these OpenFlow feature request messages. And in the bottom pane, you can actually look inside. You can actually look inside like what is inside the message. So feature request message usually doesn't contain much information, but if you look at a feature reply message is actually from the switches to the controller. So the switch actually puts up like all of its features, like what are the ports, what are the capabilities, number of flow tables supported and whatnot. If you remember, like when during our last class, we did a OVS OFCTL command, right, on the switches to show what is inside the switches. So essentially, the switch actually puts together all those information and sends it back to the controller through this feature reply message. So if you just select one of the messages, which is like tagged as OFPT feature reply, and go to the bottom pane, and expand on this OpenFlow 1.0 tab, you'll actually see the content of the messages. So for example, sends a data path ID, number of buffers, number of tables, and also information about different ports of the switch, port number, MAC address, and so on and so forth. So this is an example to demonstrate that how the messages look like, the message exchanges look like. So there are many other messages that are exchanged between the controller and the switch during the operations. For instance, we'll see packet in message and flow mode message later on. So now from here, let's get back to our controller. All right. So at this point, we are able to at least communicate with the switches using OpenFlow, correct? We can see the devices. All right, it works. We can see for devices. Sorry. Okay, I'm trying to find my mouse here. So at the same time, we can actually list a bunch of other information from ONOS CLI. Like for instance, ports. So ports is it's a side effect of the switch discovery part. So it will. Okay, again, my output is very broken. So let me just select a part of the output. Okay. No. So ports will show the different ports that are present in the switches, like all the switches. Like in this case, it will have like 4 different sections for all like 4 different switches. So if you remember, this is very equivalent to running like the CLI command, OVS, OFCTL, dump ports that shows you the information of the ports. So instead of directly running the commands on the data path itself, this is the control plane, which has this global view of the devices and as well as their different characteristics. So one example here is the ports, right? So was everyone able to see the list of ports of the different switches on the MiniNet network? Did it work for everyone? All right. Laval and Toronto? Okay.
Toronto's good.
Good. Okay. All right. Laval? Okay. All right. Okay. So we're on the same page. There is another command called hosts, which unfortunately didn't show anything. We'll come back to that. There is another command called links. Unfortunately, that doesn't show anything as well, right? The reason being, so OpenFlow has these messages for the control plane to communicate with the data plane, right? And that's how the control plane discovers the switches, the network devices. But there is no OpenFlow messages defined for discovering the ports, the connection between the switches, in between the switches. So for that, we need to run a separate protocol. Like for example, there is this protocol called Lightweight Link Discovery Protocol, or LLDP. So that discovers the links in the network, right? So to have a full view of the topology, we need to discover the hosts, the links, and the switches, like all of them. So right now, we have information only for the switches, not the links yet. So what we need to do is we need to load another application. That application will run this LLDP protocol to discover the links in between the switches, all right? Once we load the application, we should be able to see what are the links that are present in the network. So let's get back to the slide. Okay. So we will now activate another app. Okay, so we activated our LLDP provider app. So LLDP provider app will essentially run this, execute this LLDP protocol and discover the links. So if we execute links now, this command from the CLI, we should be able to see the list of links, right? Previously, we were getting an empty list, but right now we have a populated list of links that shows, okay, what are the links present in the network? Did everyone see the links? Right, other places? Okay, worked out okay? Okay, all right. So let's have a look at what links we have. So if you remember the topology, let's get back to our topology. So we had 4 switches. So there are 3 links in between them. And each switch has a host connected with it. So there is a switch to host link between link present as well. However, ONOS will show us only the inter-switch links, right? The links that are in between switches, not the hosts. So we should see 3 links here, but we are seeing more links here, right? If you count, it actually shows double the number of links because it shows link in each direction. This is how the protocol works. So you discover link and you discover link in both ways. So for example, the first link shows the source interface, the destination interface, and some metadata. If you look at the second link, it is actually just the reverse of the first link. Again, shows the source interface, which is exactly same as the destination of the first link. And similarly, the destination is similar to the source of the first link. Yes, we have a question here. In what? Is it ever possible for there to be a one-way or will it always? In this case, the links are actually always symmetrical. The links are symmetrical. Right at this moment, I don't remember if it is possible to make a link like a one-way link, but usually links are like by default like full duplex links, like symmetrical links. Any other questions? No, okay, all right. So now one thing about the format here, so if we just take one endpoint as an example, so this source interface, it is actually specified as the switch ID / the port ID. So this means that this is port 2 of switch ID OF : a lot of zeros and 1. Similarly, this one, the destination, it represents like port 2 of switch ID this. So this is how it is. Links are usually represented. So at this point, we have the switches. We have the links in between them as well. So let's try to see if we still have the hosts or not. We still don't have the hosts. Okay. So we'll come back to slide 13, but let's go to slide 14 first. So in order to discover hosts, again, there is another application that discovers the hosts or keeps track of the hosts. So let's try to activate that application first. Okay. So we have activated the application. Now, so in this case, the endpoints or the hosts, they don't run any protocol, right? They are not part of LLDP protocol in this case. They don't communicate with OpenFlow using, they don't communicate with the controller using OpenFlow as well. So the only way the controller knows about the host is when the host, they actually send traffic through the network. When they send traffic through the network, the controller receives packet in messages, and those contain information about the hosts. And that's like from a very high level, that's the high level way for the controller to know what are the hosts are, what are the endpoints in the system. So this means that even though we activated the application that keeps track of the hosts, running this host command, it will not show us anything, right? We still have an empty list here. So let's try to send some traffic from Mininet, right? Let's try to do a ping all. Let's get back to our Mininet console and do a ping all from here. So ping all will send an all-to-all ping request, right? So this means that we should be able to discover all the hosts. But if you run ping all, it's highly likely that it will not work, right? So because the hosts are trying to ping each other, but as you can see, they are not able to ping each other. The ping message is not going through. The reason being, again, there is no application that does the forwarding. So we need an application that will actually do the forwarding, like set up the paths whenever they receive a packet in message, because otherwise no one is actually handling the packet in messages. So let's activate another application for forwarding. And that would be on slide 13. So there is this application called FWD, short for forward. Where is the window? Okay, so we activated the forwarding application. So let's see if some of the ping work or not. Yes, so as you can see, as soon as we activated this application for forwarding, although previous ping between hosts, they did not work, but as soon as the application was activated, now the remaining pair of hosts, they were able to communicate with each other, because now there is some application that is responding to the flow setup messages. And let's get back to our ONOS window and see if we can find some hosts. Yes, so we do have some hosts here, and there are 4 of them. So I'm selecting one of them for convenience. Where is it? Yeah. So we have 4 entries like that. So ONOS was able to discover all 4 hosts, because I think for the rest of the ping, like pair of pings, all 4 hosts were involved. And it has the information about the MAC address and the attachment point of the host as well, like so which switch port this host is attached to, and unfortunately not IP addresses. And as you can see, the MAC addresses here, they kind of correspond to the host ID. H1, H2 has MAC address like 1, 2, 3, 4. That's because that's how we started Mininet, right? That's how Mininet was set up. So everyone was able to see the hosts on their machine. Worked. Other schools, it worked for you as well? Okay, all right. So I saw many thumbs ups. All right. So at this point, definitely there was packet in messages and flow mode messages in the network, correct? So packet in messages were for setting up the path for the flow, and also flow mode messages for actually setting modifying the flow table. So let's go back to Wireshark and see, just to have a look at the messages. So I have a filter here on slide 13 that will just filter packet in messages and flow mode messages from the packet dump we have. Wireshark. So let's clear the existing filter, put the new filter and apply. Okay, so if you click on a packet in message, so if you click on a packet in message and expand on the open flow tab in the middle pane, you'll see some information inside the packet in message. For example, you can see that, okay, what is the reason that this packet in was sent? Because there was no flow table entry that was matched. Sometimes the controller installs a rule that if there is a specific packet signature, always send a packet in message to the controller to inform the controller that there was a packet of specific type, regardless of whether there was a rule or not. So for those packet in messages, we'll see like a different reason here in the float and in the packet in message. And also the controller, the switch included a part of the header here as well, like the Ethernet layer header, the IP protocol header, and the IP protocol, correct? Yeah, the IP protocol header as well. So this is like just one instance of a packet-in message. So let's look at a flow mod message followed by this packet-in message. So if we expand on the OpenFlow tab of this flow mode message, you will actually see the information inside the message, like how the flow table should be programmed. So essentially, it usually has a transaction ID to keep track of, okay, which message was used to modify what entry. And here we have the flow signature. If you recall that how flow signatures look like from the first lab exercise, we can have like input ports, Ethernet source destination addresses, protocol type, and whatnot. So you'll find many of those fields present here as well. For example, we have input port here. We have Ethernet addresses, VLAN IDs. In fact, we also have some idle timeout and hard timeout for the entries as well. So when the timeout is 0, this means that this entry should not be evicted. So yeah, so that's an example of how the message looks like. So packet in for flow setup that contains the packet header and additional metadata. Similarly, packet flow mod messages, which is for programming the flow tables themselves, that will contain the flow entries on how to program the flow table. The switch receives it, processes it, and programs the flow table. Okay. All right. So I think at this point we can actually close Wireshark, because we'll not be using Wireshark anymore, and it kind of slows down everything quite a bit. So let's quit without saving our capture, and done. Okay. All right. So let's sync up at this point. So what we have seen so far is like different features in ONOS controller. They actually depend on the different applications. So if you need to have that feature, we just need to load the application and we'll have that feature. If we disable the particular application, we'll lose that feature. For example, if we disable like forwarding application here, we'll not be able to forward anymore. Right? If you disable it and do ping all, we'll see that, okay, ping is not working anymore. So let's do a quick exercise to get familiar with the applications, like a 10 to 15-minute exercise. What you need to do is first deactivate all the applications that we deployed. So start from a clean slate. Then deploy a small topology that I am showing here on Mininet, and then activate the necessary applications to make sure that you can, when you run devices, links, and hosts, and ping all, like all of them work. So when you run devices, you're able to see the list of devices. Again, similarly, able to see the list of links and hosts, and also able to ping between all pair of hosts in this topology. So it should not take too long. So probably between 10 and 15 minutes. So give it a try. And again, like if you have any questions, feel free to ask. Oh, there is no grade assigned to this exercise. This is just for getting familiar with ONOS. So everyone did okay? It worked? Okay. So other schools, any questions? Things worked okay? Okay. Toronto, Laval. Okay, then let's resume the remaining of the session. All right, so let's get back to the VM. So the other things we can like query from the ONOS CLI are, for example, like like what are the flows that are installed on like all the switches. For example, again, my output is all over the place. Excuse me. But let's take one device, for example. So when we did this flows command, it will like shows like concatenate the flow entries of all the switches. For example, here look, we are seeing the flow entries of switch 1, which it is saying that it has 5 entries. So, and if we take one entry, for example, okay, so here, the things we are interested in are this field. So there is a field called selector. Let's take this one. There is a link. There is a field called selector. So selector actually defines the match of a flow. What are the protocol fields? What should be the value of different protocol fields to match this particular flow entry? Each flow entry has a unique ID that is assigned by the controller itself. So for instance, in this case, the selector is if the Ethernet type of the frame is LLDP. So this is essentially for the LLDP packets that are going in the network for LLDP protocol. Then take the action here that is under treatment. So remember, like the flow matches. So flow matches are here like selector, but again underneath there's like essentially open flow flow matches. Treatments are essentially like actions taken by open flow switches. So in this case, what it is saying is that if the switch sees a LLDP message, then it will actually output the LLDP message to the controller. Okay, so that's usually how LLDP works. The packets, they flood through the net, keep flooding through the network, and each switch, whenever it sees a LLDP message, sends it back to the controller. The controller accumulates all the LLDP messages received from different switches, different interfaces, uses all the metadata to figure out what are the links are, how the topology looks like. But again, that's something completely different. But this is an example that not only that our action can be to output on a port or drop a packet or modify a header, but the default action for a packet can be just to send it back to the controller. So the controller can take action on that. And even for these packets, we'll actually see a lot of packet in messages being generated. If you open Wireshark, you'll see that every like now and then there is like a packet in message captured because of these LLDP messages. Because LLDP is run like periodically, and when it is executed one time, many packets are flooded to the network, and for each packet, the controller gets a packet in message. Okay, so again, there isn't much to say about the flows. We have already seen that before. So let's query some statistics from the control plane. So there is this ONOS command called get flow stats. So get flow stats will give you statistics regarding the flow entries. Oops. So after get flow stats, what we need to specify is the switch entry, the switch ID. For example, we are specifying here the ID of the first switch. So what it will show is, again, okay, can I identify a flow? All right, so it will show the instantaneous rate of the flows. Right now, there is no traffic. That is matching the rules. So in most of the cases, you will see that the rate is not valid or set to 0. But let's push some traffic through the network. Say, let's run iperf. Right. That will be between H1 and H4. So now if we look at the statistics, still 0. That is strange. Okay. Let's look at the flow stats of another switch. Flow stats of 0. Summary flows. Load not valid, unknown. Total load, immediate load. Okay, let's try iperf again. And let's have a look at the statistics again, but unfortunately it's not showing anything. And at this time I don't have a solution for that. In unknown load. So like, can anyone see any numbers like when they execute get flow statistics, or everyone is seeing unknown or like 0? You have some numbers? You have some numbers?
It's for a short time.
Yeah, it's supposed to be very short time because it's instantaneous, like instantaneous statistics, right? So when you run iperf, it is executing. So you take the statistics like it's like a snapshot of like one time. Other people, like, are you seeing any statistics when you run get flow stats? Yes, no?
Yes, now.
No?
Yes.
We see some.
Okay, you see some statistics. Okay, yeah. So again, the thing is like the statistics, they can be like transient because we are sending like a flow for a short time. So when we like query a switch, we get a snapshot of that particular time. So
Siabot?
yes.
We should run ping between us to have some statistics.
Sir, can you speak up again? The voice was not clear.
She want to say that we have to send some ping, ICMP between hosts.
Oh yeah, right. Okay. Yes, of course. Okay, let's see if we can see some stats now. Okay, from my end, I'm actually still not seeing any statistics. Okay, anyway, but the idea is as long as the students can see statistics, it's working. So I guess like most of the people are able to see like some numbers when they do like a get flow stats. Yes? Okay, all right, okay. So yeah, essentially it is supposed to show you the statistics of the flow at like a particular time instance, and that's basically what it is. Now so far we have been querying the switches, right? Or getting information out of the switches. So we can also like perform operations on the switches as well. Like, for example, like when we executed the forwarding application that was modifying the flow tables, right? So from the control plane, we can actually enable and disable, say, for example, switch ports. So that can actually take down a link. So for that, the command would be something like this. So let's clear it up. So we are sending a ping already from host 1 to host 4. Let me restart the ping. And let me take down the link between switch 1 and switch 2. Okay. So for that, let's see what are the links are. So port 2 of switch 1 is connected to port 2 of switch 2. So let's take down port 2 of switch 1 and see what happens. So this port state command, it is used to modify the state of a port. So for that, first, oops. Wait. Switch ID and port ID. Okay, ports. Okay, sorry, I think there was a typo in the slide. There should be no dash. Sorry, there was a typo. There should be no dash here. So port state, and then we specify the ID of the switch, in this case switch 1, and then the ID of the port, that would be port 2, and then enable or disable. So let's disable the port. Now if we go back to our mininet window, so at some point we should see that destination host is unreachable. Well, at least ping stopped working. So did ping stop working for everyone? Like when you take down the port, ping should stop working. I mean, you should not see any response like a message in your ping window. Did it happen for everyone? Yes. Other places? Yes.
Yes.
Yes. Okay. All right. Now, if we again like enable the port. Oops. Instead of disable, if we enable it again, let's see what happens. We get back the ping messages, right? Okay, at other places? Yeah. Here, Waterloo, you saw that, like take down the link, ping stopped and started again. Okay, all right. So let's stop this thing. All right. So there are a number of a few other commands for querying the switches. So I'll not go through them, go through all of them. Just practice at your own pace. So right now, the thing we'll discuss is intent. So as I said like earlier during like the initial part of the lab. So the idea of an intent is that from a high level, an application specifies what it wants from the network. Right? Like a very basic example is connectivity intent. That we specify two hosts and we say that, okay, we want connectivity between host 1 and host 2, for example. Now, from the application's point of view, it doesn't really care about how that connectivity is ensured, what kind of flow rules are installed, what is the exact path. If the path breaks, what happens? If the path is rerouted or whatnot. From the application's point of view, the application really doesn't care. it is taken care by the controller itself. The controller installs the flow rules, necessary flow rules to set up the path to ensure connectivity. It monitors them. If the path breaks, then definitely the controller tries to reroute the flows along the path between the hosts to make sure that the intent is always satisfied. But again, it can fail at some point because, say, for instance, there is a partition in the network. In that case, definitely the controller cannot set up any path, right, between the hosts if they are on different clusters or islands. So let's try to do the same thing using an intent. Try to specify an intent to ensure connectivity between hosts, and then take down a link between on that path and see what happens. So where am I? Okay. All right. So let's clear this window and go to a terminal. So I think so if you go to the directory that you cloned from Git, I think inside the directory you will find a directory, another directory called Onos app samples. So inside the directory, there is a sample application that uses intent. So what we'll do is we'll load the application in Onos, activate it, and try to use that application. So far we have been using this forward application. This is called iForward, intent-based forwarding. Now, where is that? Where is my mouse? Okay. So, okay. All right. So this is the command to load the application into Onos. So you'll find the command. So you have the setup script, right? The script that you executed to set up Java and everything. At the end of setup script, there is actually the command that failed because Onos was not running at the time. So because Onos needs to be running for this command to work, for an application to be loaded. So right now, Onos is running at everyone's machine, I'm assuming that. So execute this command from your CLI. Okay, so I'm seeing already installed because I already installed it, but otherwise you'll see like a JSON message. Okay, maybe I am, okay. Okay, let me increase the font a bit more so that it's easier to. Oh, I think this is maximum. Ah, I see. Right, this is maximum. Is my screen visible? Yeah, okay. Yeah, I'll just wait a minute for everyone to sync up. Just try to run this from this directory. Go inside this Onos app samples directory, and from inside that directory, execute this command. It will load the application into Onos.
Hi, the user is saying this command is not.
Sorry, the voice is very unclear.
The command you're showing isn't in the PowerPoint. Can you add it?
Hello? I cannot hear you properly. The voice is very unclear. Can you in fact like write a message on the group chat? Probably I can see it there.
Okay.
Do we need to run that command with sudo?
Yeah, it doesn't run without sudo.
You don't have to run it as sudo.
But some of us have to run with sudo, otherwise it won't work. So when you run the honors app,
Sudo,
okay.
So did you run Onos with sudo?
yes.
Yes.
Okay, so in that case, yes. But like for Onos, you don't have to run Onos as sudo. You can just execute Onos as a regular user. But if you executed like ran Onos as sudo, then yes, this one you have to run it as sudo as well. Otherwise, it cannot communicate. So everyone was able to load the app. Yes. Yep. Worked okay for other places. Did it work okay for other places?
Anyone got it working?
Yes. No.
No.
Okay. Can you please say what are the issues? So, okay. It should be inside the directory that you cloned. Like, so are you having troubles in Toronto? All right. Okay, so moving forward then, I think the issue is resolved. So once we have the application, so let's first disable or deactivate the regular forwarding application. App deactivate org onos forward. So let's first deactivate our regular forwarding application before activating the intent-based one. That's one thing. And the other thing is the topology that we have right now, it doesn't have any alternate paths. So let's deploy a topology where there is an alternate path between a pair of hosts. So let's take this topology down. Let's deploy mininet with tree topology with depth 2 and fan out 2, 24, and the max are initialized. Okay, so we took down the previous topology and deploying a tree topology. So this topology is exactly the same one that was part of the exercise in the current slide. So we have a tree topology, but again, like tree topology doesn't have an alternate path in between switches, right? So let's add another link to make it a triangle. So if we look at the topology, what I'm going to do now is, okay, so we're looking at the topology at slide 15. So the root node is switch 1, and the other nodes switches are like switch 2 and 3. So I'll put a link between switch 2 and 3 from mininet. So there is a command in mininet called link, and you can manipulate links with this command. So between switch 2 and switch 3, let's. Oh yeah, right. You cannot. I forgot about that. Yeah, never mind. Okay, let's not use this one. So I have a topology file provided as part of the scripts. Let's use that one. So inside NetSoft Tech Labs, I think there is a triangle topology provided already. Oops. Okay, so inside the Git repo that I shared, inside that repo, there is a file called triangle_topo.py. Just execute the file as a super user. It's a Python script. It's a mininet Python script. So it will deploy a triangle topology where each node has 2 hosts attached to it. So essentially, it's similar to the one shown here. Similar to the one shown in the slide, except that there is an extra link between switch 2 and switch 3, and also each the other switch 1 has 2 more hosts attached to it. So that's our topology for now. Now let's activate the intent-based forwarding application. So that would be app activate org onos ifw I forward. Again, the command is given in the slide as well. That would be in slide. That would be in slide 17 to the command to activate the app. So let's activate the app. It's activated. So the app allows us to look at intents. There is this command called intents -i. Okay, so there is no intent here right now. So what we'll do is, okay, just check another time because, okay, all right. Hello?
I think we should rerun Mininet.
Yes, I got the intent -i.
You need to rerun Mininet because?
Because we activate after the we activate the module after.
Oh no, that's okay. That's okay. It's fine. I mean, because these two are like independent. So what we need to do is we'll add like an intent right now. We haven't added any intent yet. So we'll actually add an intent right now, saying that, okay, ensure connectivity between these two hosts, say host 1 and host 4. And let's see what happens after that. So let's go back here. For that, we'll use this command add host intent. Right. So add host intent. What it takes is, wait. Okay, let me check if there are hosts or not. Oh, there are no hosts. Okay. Since there are no hosts, we have to go through a painful process. Okay. So yeah, we deployed a new topology. So we need to do a ping all to make sure we can identify the hosts. So we don't have the forwarding application, but we have an intent forwarding application. The intent forwarding application actually handles packet in messages as well and adds default intents in the controller to make sure that the all pair communication works. So if we do intents -i now, I think we'll see a lot of output. 1, 2, 3, 4, 5. Okay, there is a lot of intent by default installed by the app. It's really hard to track. Let's try to see something else. Okay, we have the list of hosts. How about if we deactivate the app? Because the problem is we will now add intent by ourselves. So if there are intents already existing, it's hard to figure out like which is our intent and which is the intent was already there and whatnot. So let's deactivate the app. Yeah, okay. Probably there are no intents right now. Sorry. Oh. Oh, okay. That is a problem because ONOS doesn't have a very easy way.
Should we rerun the honors with some option like clear cache or something like that?
That is an option. Okay, let's try. Okay, let's try another thing. Let's try a hack, maybe. Okay. Just give me a second. Where is my mouse? Okay. All right, so let's try this command. Okay, cool. Finally, yes. So let's execute this command. Where did my mouse go again? So let's execute this command, remove intent, with the option -p, and then the application name. So this will delete all the intents installed by that application. So once we have that, what we'll do right now is, okay, we'll do the following hack, okay? Because from here, in order to install a host intent, the hosts, they need to be identified by ONOS, right? And they are not identified as long as there is some forwarding app handling the packet in messages from those hosts. So let's first reactivate our forwarding app to make sure we know the hosts without necessarily populating the intents by the intent application. All right. So let's app activate org ONOS project forward. That's activated. Oops. Ping all. Okay. So I think hosts, we have all the host information of all the hosts. And so this is the ID of the host. So this ID field, this is the ID that we'll be using when specifying a host intent. So now let's deactivate our forwarding app and reactivate the intent-based forwarding app. Okay. All right. So now let's add an intent to ensure connectivity between a pair of hosts. So let's pick, okay, let me go to the slide. So let's pick a host from this switch. This would be S2 here, or if we consider that S1. So from host 1, so for switch 1, the hosts are host 1 and 2. For switch 2, hosts are host 3 and 4. So let's ensure an intent between host 1 and host 3, right? And let's see what happens. So hosts, to get their IDs from here, and then add host intent. So for add host intent, we first need to specify the name of the application itself. Or no, okay, all right. So for host intent, what we do is we specify the ID of the hosts. We're saying that, okay, this host and this host, they should be connected. So let's take host 1. And host 3. So host 1 and host 3, we are adding an intent in between them. So the intent was submitted to the intent framework that installs the flow rules and whatnot. And let's check in the list of installed intents, and we have we should have 2 intents at least. Yeah, one intent, yes, because we specified 1 intent. So the intent is there. So we have something there. So we installed an intent saying that ensure connectivity between host 1 and host 3. So let's ping in between just host 1 and host 3. So h1 ping h3. Well, it works, right? Because the intent is making sure there is a path. Now, let's check the path here. So there is a command that allows you to see the path between 2 switches, right? So now host 1 is connected to switch 1, and host 3 is connected to switch 2. So let's give the ID of the switches, and we can actually see the path. So the path consists of here just 2 nodes, like a single hop path. That's why the cost is 1. Now let's take the link down between these 2 hosts. So between S1 and S2, let's take the link down. Okay. And let's try to ping them again. We're still able to ping the hosts, right? Although the link was taken down. Now let's check the path again. So now we have a longer path in between these 2 switches. So before it was a direct path, like a one single hop path between switch 1 and switch 2. We took the link down. We did not do anything else. We just had an intent that, okay, always ensure connectivity between this host and this host. So the controller automatically took care of handling this link failure. So it created an alternate path between the other switch, right? And that's why we have a path of length 2 or cost 2 here. As you can see, this path goes from switch 1 to switch 3, and then from switch 3 to switch 2, right? So that's how intents work, and this is an example of a built-in intent. So clear to everyone? Any questions? Was everyone able to do that on their virtual machines here in Waterloo and also in other schools? Sorry, we had a bit of mishap in the beginning, but was it okay for everyone at the end? Okay. Laval, Toronto? Here? It's okay? Things work for everyone? All right. Yes. Sorry, is there a question from Toronto?
No.
No. Okay. All right. So now moving on. So the next thing we'll be looking at is the REST API. So ONOS exposes a RESTful API that can be used to both query the devices as well as modify the devices at the same time. For instance, installing flow rules on specific devices, bringing up or down a specific port. We can list the links and the ports. So essentially, we can get the whole view of the topology, and we can do everything from the REST API. So let's try to execute at least a few REST APIs before the class, the lab class ends. So I've put a reference to the a ONOS REST API at the end of the lecture. That is on slide 19. So there is a link that list all the API that ONO supports and also description, parameters, and whatnot. We'll just have a look at a few of them, how we can use them. So the base URL looks something like this: localhost, and the REST API server listens on port 8181, and the root has a few other like REST components. So let's first try to see if we can see the list of devices by calling a REST API. So the REST API is a password protected API, although the password I have put here is in plain text. So the password, the username he is Onos, and the password is rocks. So essentially Onos rocks. If we go back to our VM and try to call an API, so let's open a window. And let's just try to call an API, like one of the REST APIs. So this REST API will query the list of devices. So we should be able to see an output, which is not very pretty at this moment. Let's see if we can copy it and get a JSON formatter or something. And I guess that's a bit better. So everyone can see that, or maybe can I? Yeah, I can zoom in. Okay, so when we call the REST API, it like responds by providing JSON objects, JavaScript objects. So for example, it provides an array of devices that is present in its internal local database, and again, like gives all the details information. I'll not go through the details because this is pretty much the same information that we saw when we executed devices command. Pretty much same information, just packed in a different format. So one thing let's try to do as the last exercise is see if we can install a flow entry in a switch using the REST API, because the other API calls, they're very much similar in terms of functionality, that what they can do. Like most of the CLI functions that we saw, they actually can be done through the REST API. Like for instance, listing the ports and the links and whatnot. And even like reading the flow table entries of different switches and all these functions. So to add a flow rule, we have to make a HTTP post call to the REST API server with a JSON file that describes the flow entry. All right. So the JSON file has a format to specify what would be the match fields of a flow entry, what would be the actions taken by the switch when when there is a match, so on and so forth. So let's try to first deploy a simpler network where we don't have to install a lot of flow entries. Maybe we can deploy minimal. Like minimal topology. Yeah, so we added like deployed a very minimalistic topology, like one switch and two hosts. So we'll just make sure that host 1 can somehow communicate with host 2. We'll add a port-based flow rule, similar to the one we did before. But this time, instead of going through into the switch using OVS commands, we'll try to add it through the REST API. And let's see how that goes. So let's disable the forwarding applications here. to make sure that there is nothing else setting up the path. App disable, oops, not disable, deactivate org honos project, I forward. Yes. Okay, so that's deactivated. And yes, no other application is there that can forward the packet. And also let's check. Yeah, ping doesn't work, so nothing else is setting up the path. Okay, all right. Now, inside the Git repository, there is a JSON file provided. So there is a template file that is provided inside the Git repo, like flow rule template. So let's try to open that file. Okay. I think I need. Can everyone see my screen? Or the text is probably very small, right? Okay. Oh, that's the VM menu. Sorry. Edit preference. Oops. Okay, I'm just increasing the font size here. Probably better. Okay, so we'll be passing a JSON object to the controller that defines how we want to like modify the flow table. So there are some fixed fields for flow entry, like the priority, what would be the timeout, and whatnot. But what we are mostly interested here is this, and also we need to specify like for which switch this REST API is being called that we want to modify the flow table. Again, we have one switch, and the data path ID is all01. So two important things are, first of all, how the flow will be treated, and what are the selection criterias, right? So these are the two things that we need to specify here. So first of all, we are selecting based on input port. So right now we have one switch and two hosts. If there is a traffic on input port 1, we want to send a traffic to input port 2, and vice versa. Like if there is input port 2, we send it to input port 1. So let's create first one rule that says, okay, I think this one kind of does that. If there is traffic on port 1, we are matching on port 1 here under this selector object. If you remember, like ONOS has this selector field, which essentially contains the flow signature. And then there are these instructions object, which contains the actions that will be taken when the selector is triggered. So let's try to pass this object to the controller. I think I have the command here. So let's copy the thing. Okay, probably open another window. All right, I think our JSON file is, we have the JSON file, right? Flow rule template.json. Okay. A few things we need to figure out. So first of all, the file name that contains the JSON object. Sorry, template, flow rule template. Okay, post nodes v1 flows, and then the device ID. Okay, the device ID should be here in the JSON file. That's the device ID. Let's copy that from JSON file. Okay, and priority cannot be greater than. Okay, let's see what's in the priority field. Probably we put a wrong value there. Yeah, let's just put 0. Doesn't matter at this point. And make the API call again. Okay, so there was no error. So most likely, hopefully, it was installed. We can actually check, right? We can, in fact, quickly check from here. For switch 1, let's dump flows. Oh. So where is yeah, so this is the rule that we just added. Okay, so we have like one rule for one-way communication. So let's put the rule for the other way as well. That would be output port 1 and input port 2. Let's save the JSON file. And make the API call again. All right. So at this point, we should be able to send pings. No, not really working. Why is that? Or did we? Okay, let me check. So what are the rules? So these are the two rules. If import is 1, then action is. If import is 1, then the action is output should be on 2. Input is 2, the action is output should be on 1. Did I miss anything here? Nope.
Maybe the priority.
That is a possibility. Okay, let's. But there are no other. There are no other packets that is. There are no other rules that match these packets. Is everyone getting the same issue, like not able to ping even after installing the rule, or is it just me? Other people are also not seeing any like ping replies, like ping is failing. Yes? No? Okay, so everyone is seeing failed pings. What else can be an issue? We can change the priority and see.
Can you go both ways? Because the file says that it goes from port 1 to output port 2.
Yeah, we added 2 rules, right? We added 2 rules. One for like if there is packet on port 1, it goes to output port 2, and also vice versa. If there is packet on port 2, then it goes to output port 1. Oh. I hope I'm adding rules to the correct device. Okay, let's stop the topology and clear mininet. Oops, sorry. Okay, let's take the topology down and clear mininet just in case. So, okay, there is nothing here. Let's deploy mininet again. And let's also disable the topology discovery service. So that would be app d, oops, deactivate LLDP provider, just to make sure that the switches don't have rules for forwarding the LLDP packets. So there is no rule in the switches at all. And deploy the network. All right. So at this point, we should have only one bridge in this system. We have exactly one bridge in the system. Yes. Now let's try to add the flow rules through the controller. So we add one rule first, and then we modify the rule for reverse path. Saved. We add the other rule. Okay. Dump flows on S1. Okay, anyway, let's check if it can ping or not. Fingers crossed. And it doesn't work. Okay. Yeah, theoretically it should work because the flow rules we added through REST API essentially says that just like send the packets like on port 1 to port 2 and from port to the other port and vice versa. It doesn't say anything other than that unless it is matching some other flow rules. That's something I need to debug at this moment. Unless it is matching some other flow rules, it should work. Probably it is matching some other flow rules and being sent to the controller. Otherwise, it's supposed to work. But that's pretty much it actually for today's lab. Unfortunately, the last thing didn't work as expected. So there will be a lab exercise that will be posted very soon for next week, which is due next week, similar to the one that we had this week. If I find a solution, I'll definitely post it on Piazza, like what went wrong. I think we are already like running out of time. Yeah, we were overrunning time. So yeah, does anyone have any question? Waterloo? No? Other schools?
Thank you.
No? We're good? Okay. All right, then we'll finish our class lab session here, and hopefully see you next week.
Thank you, Siobhan.
Okay, yeah, bye.
Bye.